Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our modern C++ series. In this lesson, we're going to be taking a look at the algorithms library, continuing looking at the partitioning portion. So if you didn't catch this previously, you can catch it in the playlist, or of course, you can enroll on courses.msha.io. This is free to use, and you can track your progress, so you make sure that you don't miss any of those lessons. So with that said, though, let's go ahead and dive into CPP reference and go ahead and check out the algorithms library. I'm going to go ahead and scroll us down past some of the stuff we've looked at here, the non-modifying and modifying sequence algorithms, and down into our partitioning operations. Now, the ones I want to look at today are the partition point in particular, and let's go ahead and look at partition copy. Now, I've already looked at is partitioned, again in the previous video, and partition itself. And there is another thing that might be worth looking at some point. Maybe there's a video. If you folks want a video on stable partition, we can talk more about stable algorithms and those types of things. Comment below if you think that would be useful. But effectively, it's going to be similar to partition, but maintain the ordering even if you have duplicates. That's the idea with a stable algorithm. You can just kind of say it in a sentence. But I want to look at partition copy and partition point here. And let's go ahead and look at partition point first and foremost. And basically what this is it's going to examine our partition here. So we're going to basically look from the first to the last element here. I'll go ahead and actually highlight the const expr version that we have in C++20. And basically evaluate that predicate and return the first point that matches, or rather indicates that it is not satisfied by whatever our predicate P is. Okay, so for example, and we had this example from the last time here, this top example here is successfully partitioned around this predicate, elements less than 4. I've got a left side and a right side. There's two clearly divided sides here. But on this side, however, we aren't going to have that here. So in this case, I believe it's just going to give us back 7. We're going to test it out here because that's the first point that doesn't satisfy the partition. Now, this is where it might be useful to check again if our actual collection here, whether that's a vector, list, whatever our container is actually partitioned. Okay, so we wanted to learn that is partition first and foremost. So we'll try to play around with that a little bit and get the partition point. Now, how we might use that though? What is the point of this partition point? Well, it can be useful to try to figure out, once I have the partition point, which returns me an iterator, maybe where that is in the collection. So for example, typically we want sort of even size partitions. Again, this just depends on the problem you're trying to solve, though. I'll say that. So that's a huge sort of generalization. But typically we want, in something like a quicksort, which you study, is to be able to divide some container, some collection, some amount of computation into two, because maybe you can split it up or parallelize it or something. Maybe you'll just want to use the partition point to figure out if I've got two threads looking at stuff, to look at the left side and the right side and just figure out what that sort of divide is. So again, a lot of different ways that you can think about this if you've got your container divided in some way. Now you could just use size divided by 2 in that case and sort of figure out if you have something like a vector where exactly that is. Meaning the halfway point, but you kind of want to see maybe if your partition's close to that, right? So whatever your predicate is maybe a good way of dividing up work. So a couple of different ways to think about that as a problem. So anyways, we have this nice building block here to help us, okay? So let's see what else we got here. Okay, on the return value, of course, let's see, iterator past the end. Okay, so it could be the last element here, okay, if it satisfies the predicate. For everything, right, that means we don't really have a partition, we just have all of like a left side or a right side. As far as complexity, let's see here. Given n, we perform log n applications of the predicate. Okay, interesting. And that would be for... we'll want to look at sort of a implementation of this here. But if I have random access, I suppose I could do some sort of, I mean, anytime I've got to log in, some sort of binary search effectively to see where that pivot point is here. So that's kind of interesting. But if I don't have random access, well, of course, I've got to sort of walk through my iterator and just kind of see, you know, where is the point where things are satisfied or not. Okay, that's kind of interesting here. Let's look at this partition point here. The possible implementation here, and this is a generalization of something called lower bound here, which will tell us like where is our lower bound. I don't think we've looked at that explicitly as an algorithm here. Actually, let's go ahead and see where that falls here. Yeah, in our binary search. So that's going to be upcoming here. So that's kind of neat here. I mean, that's sort of a hint here, right? With a binary search, you kind of know what the left side is, the sort of lower bound versus the right side, which is exactly what this is. Okay, so anyways, let's look at the partition point here. So looking at our first, last, and predicate here. So we're going to be looking for, okay, from our first to last, so we compute the length here. And then we're going to say, okay, while the partition point is less than length, or otherwise we don't return a negative value, find where the halfway point is, find the middle, and just look at, well, the first half of it here, okay? And what I'm looking for and what I want to actually check here, I mean, this is telling us, do we, you know, walk forwards or backwards, basically, is if we have to have run partition on this before. Otherwise, I mean, we could sort of assume it's going to break. I sort of want to break this and just see what happens. But of course, if we run, and that sort of answers the question of why you can get log n complexity. I think this is assuming this is partitioned here. Examines the partitioned if as if by standard partition. Okay, so I think we have to run partition first. Okay, if I run it on something that's not been partitioned, we can't get that point back. Okay, so that's kind of interesting. Now this might be a case actually. You know, we think about these building blocks here where you might want to actually optimize and write a partition algorithm that maybe caches or stores the point where something is. You know, you could have basically two overloads of this. One that returns, because let's see, partition, let's see, what was the return value here? Okay, it gives you the forward iterator here, Okay, and the iterator to the first element of the second group. Okay, so you do have this partition point already, that you can get the iterator just by running partition, okay? I was thinking maybe you want, I guess this is just the way to get it back here. Okay, so we kind of have that. This is kind of interesting here, because we could capture that point here after running the partition here. But I think, let's see, just kind of thinking out loud here, what we could do is, well, again, we get flexibility here because we've got iterators here. So if we wanted to run or capture the partition point here, or if we've already tested is partitioned, and not want to have to run this algorithm, right, and just gather the partition point, that would be a use case to use it. Okay, so it makes sense to have these in different blocks and not just run partition over and over and over again, because you're doing lots of swaps and moving stuff around in memory, which might be great. It might just be better to say, okay, we already know we're partitioned. Maybe you lost what that partition point was or whatever, and modified some data within the structure. Meaning if these are like keys and there's something else in the data and you just want to capture the partition point again later, this is useful for that, okay? So we kind of have to justify why these are useful. And then this is exactly what I'm going to want to do in our example here, which is capture, you know, the distance here. And basically I want to see if this is near the middle of our particular container, okay? For however many elements we have. If that is, then maybe this is a good partition function, okay? So anyways, with that said, let's go ahead and let's play around with this a little bit here. And what I'm going to go ahead and do here, let's go ahead and just create a vector, because I want random access and it'll be faster. I'll specify int this time just to be very specific here. And let's just put in a bunch of numbers here. I'm going to make them all unique for now, but if we had a stable partition, that would order them as needed. Let's think about what our predicate would be, p here. So I don't need to capture anything on the outside. And let's just do return, I don't know, a is less than 6 here, okay? So just kind of picking a random value here. Okay, I think that looks good to me there. And then let's go ahead and just see what happens here if I go ahead and print out the partition point. I think this is going to break it here. Partition point. So let's break things first before we get them working. B1 begin. And again, I'm calling, again, depends on where you're jumping in on my series here, but versus N1, I've started to tend to prefer the member functions. They might be optimized and so on. And then we pass in our predicate. I think that's all we need for partition point. Looks like I spelled everything correctly. But importantly, right, we need a return from this, right? That's what we're getting back here. So let's go ahead and, oops, do auto, and I'll just call that point or something. Okay, and make this a little bit bigger here for us. All right, and let's line things up here. I know some folks don't like spaces. That makes Git diffs very large. Again, just more software engineering stuff to think about here. And let's see what happens here. Let's go ahead and well, if I print out this partition point, let's see what it gives me here. P. Let's see what happens here. Let's see if it just crashes here, because this isn't partitioned here. I wanna break things a little bit here. Okay, let's go ahead and compile that. What have I done here? Oh, missing my semicolon and my lambda. There we go. I compile. And it gives us 1 here. Okay, so 0, 1. That's the partition point here. Let's squeeze in some other element here, 2, and see if that moves our partition point around here. And we still get 1 here. Okay, interesting. Oops, and oh, that's why here I'm printing out P instead of the point. Let's go ahead and fix that up here. Point, there we are. See if it gives us the actual, what it's giving us here. 9 here. Okay, interesting. It's giving us a bunch of stuff here, So the point here is, let's see, probably not very useful here. Let's put in another value here. 7, -5, sure. Something less than 6. I'm just trying to see how this is moving stuff around here. We're still getting the value 9, so is that just like a random, let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it's just returning us the last thing here, which I imagine. So if I put 12 here, let's see, is that going to give us 10? Nope, it's just giving us 9 forever. Why is that? Well, let's go ahead and look at the documentation, see if we can understand how this works. Now, keep in mind, I'm running this with without partitioning it, so this is broken. I just want to see what the behavior is here. Maybe we should have started with the correct behavior, but again, well, that is what it is. So examine the partition. Okay, locate the end of the first partition. That is the first element that does not satisfy P, or last if all elements satisfy P. Okay, the first element that does not satisfy P, it thinks is, let's see, we're returning things that are less than 6 here. Oh, hey, this 8 here should do it. So what if I get rid of 9 here? Is that just happenstance here? What value is it giving us? 10, it thinks here. Did I mistype something? 8, is 8 less than 6? I think it's just going totally bonkers if we haven't partitioned here. So let's go ahead and partition it. Let's see if we get anything meaningful now. Let's see, partition, P1 begin, P1. And again, I'm showing you the absolute incorrect way, right? So let's go ahead and partition first, and then we'll find our partition point. Let's see what it gives us. Okay, now it gives us the right thing here. Phew, okay, now it knows what it's doing here. And we can actually figure out this distance here. So let's actually, figure out how far along this happens. Okay, standard distance here. And I need to supply the beginning iterator and our partition point. That's an iterator here. And let's capture this as the, I'm going to call this the pivot. Okay. In this particular case, pivot, it's the partition point here. Pivot, because I'm thinking about this in terms of like quick sort stuff that's less than or greater than. Let's just call it distance. Actually, that's a little bit cleaner here, or D for short here. And let's write that out here. Let's give ourselves some labels. Write out the value D here. What I'm going to go ahead and do here is, if I were to partition this particular vector, let's say get 1, 4, 2, -5 would stay the same. 8 would get swapped with something here. Okay, so 8 breaks it here. But I think I should get all the stuff less than. Then, okay, so we find our first thing that doesn't satisfy our predicate here, which is just things that are less than 6. So this is what we're going to start swapping. Okay, and I think the partition, which we looked at last time, will look for the first thing, right, that isn't satisfied, and then we start swapping. So basically, this is the first sort of failure. So 8 and 5 need to swap. So we get a 5 sort of here and an 8. And then 3 and 8 effectively need to swap. I think it's just going to swap it in for where this is here. So we should get 3, 5, 8, and then there's no more swaps that need to handle. Something like that here. Let's go ahead and compile it, run it. Let's print it out here too. I'm just going to squeeze in a for loop here for our elements here. And v1, and I'll kind of write it out nicely here. See out, elements, let's just put a space between them, and a new line at the end here. Need to start writing the back inserter with C out here. I can do it in a one-liner with for each. But anyways, there we go. So let's go ahead and compile that, run it. Yeah, the order 3, 5, 8. Okay, looks right. So it looks like it's doing the right swaps there. And let's go and see what we have here for our pivot point here. So okay, so we've got our data collection, and let's see here. We've got the distance 6, 0, or 1, 2, 3, 4, 5, 6. Okay, so that seems reasonable. 6 hops. 1, 2, 3, 4, 5, 6. And then this 8 here as the first thing here. Okay, and let's add just a random number here again, 7, just to make sure that it's working. All right, and it seems like it's working here. So again, 8 was our that remains our pivot point after we've done the partition. You can see where 7 gets swapped here. So 1, 4. Let's see, we find 3, swap that for 7. Yeah, so we kind of walk backwards here and get our elements in order. Okay, so very nice here. Let's see here. Now, a few things here. Let's, and again, this is fun to play around with, again, if it just breaks here. Right, so if I run this, again, looks like I just get garbage. Now, this time it does look like it is finding the right partition point, right? The first thing that fails, and then it tells us we've got 2 things to the left of this here. So anyways, how we might want to use this here, let's put together some of the stuff that we've learned about. Let's just do is partitioned v1 here, okay? And let's put that in an if statement here. And I think we need to do v1 begin, v1 end, okay? And or I should say, if it's not partitioned, then we want to partition it. Okay, so let's go ahead and see if that works here. Oops, what have I done here? What have I done? Let's look back at, oh, we got to supply the predicate because we want to know what it's partitioned by. Let's go ahead and compile that. Let's see, what else did I mix up here? Probably just a missing parentheses or something. Yeah, let's see here. There we go, there we go. I think we're lined up. Okay, let's see how that goes here. Compiles. Okay, partitions and runs here. Okay, so check if it's not partition it, print it out just for our sanity check here. Report the pivot point here, and then we compute the distance here so we know, yeah, roughly, you know, how much of this stuff is where we're at here, meaning 1, 2, 3, 4, 5, 6 elements here. Now let's see what is our size here. And I've got the partition point here. Partition point. Okay, I'll go ahead and just print that out here. But something that I might want to do here, again, is look at our size here. v1.size. Let's go ahead and output that. And maybe v1 size divided by 2 here. Okay. And again, what I'm just trying to show you, or it's sort of, you know, getting a use case here, if you're coming up with some function here, right, is our partition point, the distance here, 6, good or decent, right? Is it near the midpoint of our collection here? Okay, it happens to be, which is nice here. So we might consider this a good partition, okay? Right, if we just partition things at the very end, right, this is what you learn at quicksort, then it becomes like a n-squared algorithm, which is not good, right? It's going to be rare, but it could happen. So that's just something, you know, you could try here. So let's kind of wrap this up. Let's look at one more thing here. Let's see here. So we got the partition point. Oh, here's just a partition here. Here's my website. I'll show you that later. But of course, you already know about it. There it is. Let's go ahead and go back into the algorithms here. And what I actually want to do here is just copy part of that partition here. So let's go to partition and look at partition copy here. Okay. And this will be kind of like the last step that you might want to do with some sort of algorithm. And looking at this, let's go ahead with the C++20 version. Only difference with these ones, which we've gotten since C++11, is we get const expr. Very nice. Is we want to be able to copy the elements from our left and our right partitions basically into their own collections here. Okay, so that's the idea of reading this, right? Here's our whole partitioned collection, whatever it might be. Let's zoom in on that here. So that hasn't changed here. And then we want to write things to the left and to the right here. Now let's see here. I want to go ahead and say a couple things, right? If our input and output ranges overlap, undefined behavior. Okay, so if we're writing to like the same output range, right, we probably shouldn't do that. That's probably not a good idea here. So, and again, we probably want to be running with the same partition algorithm. This seems like one that could be parallelized quite nicely, right? If I'm just looking through, if I know the partition point here, you might actually just want to do std copy if you have the partition point or exactly where that partition is. Again, you can kind of think about that. If you had a lot of data, right, you could do that in shared memory with two different threads. Just some things to think about here. But let's just go ahead and use this for now, just to understand what it's doing. It's beginning of the output range, the elements that satisfy the predicate, and elements that do not satisfy. Now, this is pretty clear code, which I think is quite nice here. Oh, and there are some execution policies. Again, we got to someday look at those here. I was wondering if they could do it in parallel. It seems like something, because they're just making copies here. I believe here, right? Let's see. Yeah, copies the elements. Okay, so let's see what the implementation looks like here. Again, I guess you could do it in one for loop. So from the first, well, you're not equal to the first thing, and if the predicate is true, okay, yeah, I guess yeah, you could have this. You should run partition on this first here, but yeah, you'll copy whatever you can. And then some other stuff here. I mean, your data is not always going to be partitioned, but when it can be, it's nice, right? Maybe you could imagine having sort of a sliding window of a few elements at a time too, just looking at like 4 elements out of, if you have millions of data, and copying based off if they do satisfy something or not satisfy something. And that's also kind of something to think about. But let's just go ahead and do this with a partition here. And let's go ahead and just call some more vectors here of ints, and I'm going to call this the left side and the right side. Okay, and you can think of some clever things, right? We know about the size, we know the partition point, so don't forget all the other stuff that we could do, right? We could reserve again some memory here. Okay, exercise reserve memory to be super efficient for where we're copying into. So we're not resizing these vectors as we're making copies and so on, right? We don't want to forget about all this other stuff you've been learning in this playlist. But anyways, let's go ahead and run std partition copy. We want to run from the beginning to the end. Our output iterators, the left and the right, and then the same predicate that we've been using here, p. Okay. Then let's actually generalize this lambda here. Let's make a lambda here for printing out stuff. Let's see here. Auto print collection or something equals, let's see, take in the element here, and let's just do this here. Okay, I just want a simple like print function here for some collection here. Okay, that's the print. Actually, what am I doing? Let's just write this. Let's just copy and paste it. That's fine for this. You've seen me write this in a few other videos here, but let's just do this for the left and the right here. Okay, it'll be clear. Left and the right. Okay, so let's see what it did here. And we should probably have a new line, though. See out. There we go. Okay, so let's see if we made any silly mistakes. Oops, somewhere I put V2. V2, there it is. Make that V1. There we are. Well, let's see, did it copy our stuff here? Okay. Classic here. We should know what this error is by now. I always make it once here. Okay, I want to write to a vector. I want to write out to it. Can I just use left and right and provide the vector? No, that would be nice, but again, you know, we got to figure out how we're inserting this stuff here. Back inserter. That means I have to put things on different lines, no problem. Versus, you know, if you wanted to push in the front of the data structure, right? And, you know, talking about vectors, we usually want to push to the back, right? It's more efficient to allocate there, especially if we use stuff like reserve, okay? Okay, so let's go ahead and run this. And let's see what we got. Do we have a partition on the left where everything is less than 6? 1, 4, 3, 2, negative 5, 5. We do. And on the right, everything is greater than 6, okay? Because, or greater than or equal to, because our predicate's just a less than 6 here. Okay, so quite brilliant there. So overall, you know, this is really nice here. And again, this is a really nice, if you're, I mean, how I think about this, and again, maybe this is something worth doing some more of, but if you're solving questions for an interview or something, you can imagine having to write your whole partition operation, partition copy, checking if something's partitioned versus, you know, if you know that these things are in the standard library, this is a piece of cake to just use std partition and, again, write things out here. Again, probably worth writing out quicksort once without this, and then writing quicksort with partition. And again, it'll just be nice motivation for using your standard library. All right, folks, so there you have it. We've looked at a lot of partition through these previous videos. This one and the previous video, I should say. And if you have other questions, feel free to engage in the discussion below. Track your progress here. And as always, folks, hopefully you enjoyed that. Hopefully you learned stuff. Hopefully, you know, you're starting to put together, if you've been watching all these videos, some of the knowledge we've used, like with vectors and backsorters and other different things here. So it's becoming quite fun as we practice with this stuff. Anyways, folks, with that said, thank you as always for your time and attention. Hope you enjoyed this video, and I'll look forward to seeing you in the next one.